Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera. So we begin let's start our lecture for today. So are you good? Hope everyone in a good condition. Naka heavy rain just now. Okay, so let me record first. And before we start, okay, today our lecture will focus on analysis of variance, and we will go through this slide. Okay, I change a bit for two slides. After this, I will upload again in ULearn. Okay, then okay, let's see our ULearn. While we are learning, while we are go through this slide, we will do some exercise using R. Okay, actually I already put inside the ULearn. Okay, let me share my ULearn. Okay, can you hear me clearly?
Yes.
Okay, so hopefully everyone in a good mood, and we're already tired because just finishing from work, right? Okay, so here is MTDS Fauzia, and this is the folder that I will cover today. This is the lecture note, and I will do this R code. Okay, make sure that you download this code first, then we will run it based on the exercise given by the slide. Okay, then this is the reference book that this lecture will refer. Okay, then we go to the lecture slide. Before we continue our class, let us for Muslim, let us sedekahkan Al-Fatihah for Ayah Huzaifah. Tadi I got news Ayah Huzaifah meninggal pukul 4:05 petang tadi. So sedekahkan Fatihah untuk beliau dan mudah urusannya di dalam perjalanan balik ke Pahang. Okay. Harap semuanya dimudahkan lah untuk Huzaifah. Okay, so let us begin our class. Okay, this is analysis of variance. Okay, we will call it as Anova, analysis of variance. Actually, analysis of variance. Previously, on the first lecture, we learned about variance. Okay, if you don't remember what is variance, okay, please look at the introduction to multivariate analysis previously. I already put the definition of variance. Okay, but analysis of variance, we want to know the variance. Today we hear a lot of variant in terms of COVID variant, which is variasi of COVID, right? It's from one it is from one species. What can we call it? Is it species, or it is from one disease, and it has a lot of variants. Variants Omicron. Okay, that's we want to analyze of variance, whether the variant give the significant impact for our study or not. Okay, then as an introduction, okay, there's a lot of sentence. Okay, this is the introduction. Okay, when factors are included as explanatory variable, our focus usually shift from prediction to understanding group difference, and the methodology is referred to as analysis of variance, which is we call it as Anova. Okay, if you don't understand some of it, you may interrupt. Okay, so Anova methodology is used to analyze a wide variety of experimental and quasi-experimental design. Okay, this chapter provides an overview of R function. We will use R for analyzing common research design. R will give us summary. R will give us, by using R, it helps us to know that this factor is significant or not for our study. Okay, we want to know, for example, okay, in ours, for example, we have one dependent variable, which is we want to know the graduate employability. Okay, from this graduate employability, the factor is maybe the course that the student take. Maybe another one is intern, where they get their intern. Okay, another thing that you think possible to to give impact for graduate employability, their CGPA. Okay, or we may use the factor which is this is dependent, and this factor will be independent. It will it's not depend on anything. Okay, then from this factor, maybe we can combine, which is we want to know between cost and CGPE. Is there any effect to the graduate employability? Okay. Beside we get one factor, we have one factor, we can combine two factor. Okay, then we analyze. This graduate employability significantly this factor will significantly contribute to graduate employability or not. Okay, that's the analysis that we want to do today. Okay, is it okay? Okay. Okay, hopefully everyone will be okay throughout this, because we have 80 slides and some exercise. We will divide it. Maybe I will finish for this first part for 40 slides first. Then we continue the next Thursday. Okay. Then in addition to base installation, we'll be using the car. Is the package that we will use in R, which is car Gplot. Gplot is to plot the graphic plot for R. We will use package Gplot, package RRCOV and MB outlier package. Okay. Later we will know when to use each of these package. Okay, be sure to install them before trying out the sample code. Okay, remember previously before we use this package, we have to put if there is error when you call library car. When you want to use car, you call for library car. Okay, if there is error, maybe you have to put install. You have to install it first. Okay. Install the package double okay, this is you have to install first, then we call this library. After that we can use it. Okay, this is what this sentence means. Okay, then the next slide. Okay, this is the terminology. Okay, this is example. Okay, previously I give you example for graduate employability, right? Okay, now this is the example. Okay, For example, experimental design in general and analysis of variant in particular has its own language. Okay, before discussing the analysis of this design, we'll quickly review some important term. Okay, then this is the terminology. We will use this example. Okay, we want to know some important term. Okay, but we have to study this. Okay, studying the treatment of anxiety. Okay, this is experiment conducted for studying the treatment of anxiety. Okay, two popular therapies for anxiety are cognitive behavior therapy (CBT) and movement desensitization and reprocessing (EMDR). Okay, this is the two treatment for anxiety. The two therapies for anxiety. Then you recruit 10 anxious individual. Okay, this is our sample. 10 anxious individual and randomly assign half of them to receive 5 week of CBT and half to receive 5 week of EMDR. Okay, so we have treatment for anxiety. Okay, this is the thing that we want to the example. Okay, this is that we have to therapy for this treatment, which is CBT, and another one is EMDR. Okay, let's say we have 10 sample, which is 10 individual. So we randomly pick 5 for this and pick 5 for this therapy, which is 5 for CBT and 5% for EMDR. Okay, the duration for this study is 5 weeks. Okay, this is also for this study we use the same duration, which is 5 weeks for these two. Okay, then at the conclusion of therapy, each patient is asked to complete the state trait anxiety inventory style. Okay, then we have to measure this to complete the state. Okay, each of this individual will do this style, and this is also same trait anxiety inventory. Okay, and a report measure of anxiety. Okay, this is another one is a report for measure for anxiety. Okay, then this is the overview what this study will do. Then we want to know the terminology, the important term. Okay, then in this design, treatment is between group factor. Okay, we have one term which is between group factor with two level. Okay, CBT and EMDR. This is, we call it as treatment is between group factor. Okay, it is called between group factor because patients are assigned to one and only one group. Okay, they not share the treatment. Okay, which is they not share the therapy. Okay, so 5 group will do CBT and this 5 individual, bukan 5 group, 5 individual will do EMDR. So this is what we call between group factor. Okay, no patient receive, both. This character represent the subject of patient. Okay, style is the dependent variable. Okay, style ni, this is it. We want to know the style result. It depend on the treatment. Okay, the treatment is the independent. Okay, style depend on the treatment. What treatment that they have. Okay, then because there are an equal number of observation in each treatment condition, you have a balanced design. Okay, because we have this 5 will receive the CBT and 5 will receive EMDR. We call it as a balanced design. This is another term. Okay, balanced design. Okay, when the sample size are unequal, across the cell of a design, you have unbalanced design. Okay, meaning that if CBT receive only only 2% receive CBT, but 8% receive EMDR, we call it as unbalanced design. Okay, so we know now we already know the meaning of between group factor. And okay, this is independent variable. Dependent variable, we already know from the previous lecture, right? Okay, balanced design and unbalanced design. Okay, this thing we will see the table later. Okay. Okay, can we continue? Okay. So, the statistical design in table 9.1 is called one-way Anova because there's a single classification variable. Okay, let's see. 9.1, one way between group Anova. This is between two group. Okay, this is what we call one way between group Anova. Okay, because there's a single classification variable. Okay, specifically, it's one way between group Anova, which is only one person will receive one therapy, right? One person, one way between group Anova. This is between two group, and this is one way. Okay, then, okay. And effect in Anova design are primarily evaluated through F test. Later we look at what is the F test mean. Okay, if the F test for treatment is significant, okay, we want to know whether this F test is significant or not. Look back at the p value. If the p value is less than alpha that we we state, which is normally we use 0.05 or 0.01. So we can conclude that this treatment is significant. Okay. The mean style score for two therapies differ after 5 weeks of different. Okay, what is mean? If the F test for treatment is significant, you can conclude that the mean style score for two therapies differed after 5 weeks of treatment, meaning that there is a difference between these two therapy. Okay, so you good? Can we continue? Okay. Then the next, if you were interested in, okay, if you're interested in the effect of CBT on anxiety over time, you could place all 10 patients in CBT. Okay, this is the one which is, it depends on us, what we want to measure. Okay, this is our experiment. What do we want to measure? Maybe instead of we want to look at different therapy, we want to focus on CBT only, but we want to know its over time, which is based on 5 weeks and 6 months. Is there any different? Okay, then you can see that after you go slide by slide, the focus on the analysis of variance, we want to know, is there any different? That's the key question, which is there any different if we do CBT by over time, which is we do CBT, this is the, instead of previously we do the experiment, we divide the experiment by two therapies, which is CBT and EMDR, but here we only focus on CBT. But here we want to know, after 5 weeks, is there any difference with after 6 months? Okay, this is the two thing that we want to know over time, which is in a short time for 5 weeks and for a long time, for example, 6 months, is there any difference? Okay, then you could place all 10 patients here, 10 patient here, and after 6 months you can measure this similar person after 6 months. Okay, then this design is displayed in table 9.2, which is this is what we call it as another term within group, which is within this group 10 people, we want to measure by time, which is after 5 weeks and after 6 months. Is there any difference? And this is between group by using different therapy, a different treatment of therapy, right? Okay, so you already get a bit kefahaman on between group and within group. Okay, this is within group. Within this 10 patient, we want to know 5 week and 6 week. But between this group, okay, the different group, these two group will not receive the same treatment. Okay, but this group only receive one treatment for 5 week and another 6 months. Okay, this is what we call within group and between group. Okay, so far so good. Okay. Time is a within group factor with two level. This is the time by time just now. Okay, this is within group and there are two level, which is 5 week and 6 months. Okay, it's called a within group factor because each patient is measured under both level. Okay, so far the term that we learn is between group, within group, balance, unbalanced, and there are one thing which is one way within group, which is okay, this is statistical design is one way within group. Okay, this is also one way. Patient with time, but within group. Okay, one way within group Anova, and this is one way between group Anova. Okay, later we will look back, look what is two-way, three-way. There is other term later. Okay, then because of each subject is measured more than once, the design is called repeated measure. Okay, look here, look at this. Okay, we measure it after 5 weeks, we measure, and this is after 6 months, we measure it again. So we call it as repeated measure Anova. We want to know the significance, which is after, is there any difference after we get 5 week treatment and compare with 6 weeks treatment. Okay, if the F test for time is significant, you can conclude the patient mean style score change between 5 weeks and 6 months. Okay, so we look at the F test to know the time significant. Then we may conclude something based on this style score, the change between 5 weeks and 6 weeks. Okay, this is the measurement that they use to measure each treatment. So this for time is only CBT treatment. Okay, if you want to look at the F statistic, F value, what the definition of it, you may use this link. Okay, you may okay, maybe I have to show my screen. Oh, okay. Maybe you already can see my screen. This is statistic. How to, okay. This is what is F statistic, F value, and this is the simple definition and interpretation from this. Okay, you may see this video, and this is the sentence to you to understand it. Okay, what is F statistic? Okay, we can use R to measure to calculate it. Okay, then we go for the next slide. Okay, this is from Guru 99. the website from Guru 99. Okay, this is I think this explanation a bit good explanation what is F statistic. If we use to test if the data are from significantly different population. Okay, we want to know the F statistic. Okay, for if we have this between group, okay, this is the visualization where it is low discrimination between group, and this is where it is will be high. Okay, to compute the F statistic, you need to divide between group variability over the within group variability. Okay, the between group variability reflect the difference between group inside all population. Okay, so here the left graph show a little variation between the three group. Okay, we have the blue, red, and green group, and we can see that these three mean tends to the overall means. Okay, okay, meaning that this if we calculate the means, it will be not much different to each other. Okay, then the right part is none of them overlap. Then we can see that this is the high chance the difference between the total mean and the total mean and group will be large. Okay, this is the total mean and total group will be large. Okay, because it quite different between these three mean. Okay, this is where within a between group where it is low for F test and this is for high for F test. Okay, same goes to this. This is within group. Okay, so this is low level of variance within group. Okay, if we make this what we call blue one more uh, showing which is kita kembangkan, which is it more thinner than this, right? When we kembangkan here, we notice that high level of variance will be obtained within group, and this is for low level variance within group. Okay, you may see the explanation of this inside the Guru 99. Okay, the website of Guru 99. Okay, okay. Then we continue for the treatment for anxiety just now. Okay. If you're interested in both treatment different, okay, we want to know the difference between the both treatment and change over time. You could combine the first two study design and randomly assign 5 patients to CBT and 5 patients to EMDR and assess their study result at the end of therapy. At 6 months, see table 9.3. Okay, we want to know, okay, we want to look at over time, which is the impact of CBT and EMDR for these two groups by time, which is after 5 weeks and after 6 months. Okay, this is what this sentence means. Then, by including both therapy and time as a factor, okay, now we know that the factor is the different therapy and different time. Okay, you are able to examine the impact of therapy average across time. Okay, time average across therapy type. Okay, and the interaction of therapy and time, which is we want to know the impact, which is this is the treatment. Okay, now the impact that we want to measure, it is therapy itself. This is the therapy. And another one is time. Okay. Another thing that we want to know is therapy across time. Okay, this is therapy across time. And another, the last one we want to measure is average across therapy type. Okay. like previously, my example is cost and CGPA here. Average CGPA across course, something like that. Okay, we want to know, is there any significant for that impact? Okay, then the first two are called the main effect, where the interaction is not surprisingly called the interaction impact. This is what we call the interaction impact, which is the interaction between therapy across time and the interaction between time across therapy. And the main effect is therapy and okay, this is the interaction of therapy and time, and this therapy alone is the main factor, and this is the interaction of it. Okay. Okay. When you cross two or more factor, as you done here, you have a factorial Anova design. We have a factor, and this is the Anova factorial Anova design. Crossing two factor produce a two-way Anova. Crossing three factor producing a three-way Anova, and so forth. So we notice that there can be n factor of Anova, which is it can be 100 factor or others. Okay, when a factorial design includes both mean group and within group factor is called mixed model Anova. Okay, this is where we include in one design we have between group and we have within group. Okay, so it is called mixed model Anova. Okay, the current design is two-way mixed model Anova. Okay, here the design two-way mixed model, which is this is between group with two-way factorial Anova with one between group and one within group factor. Okay. This is the patient, and after 5 weeks and 6 weeks, it is within group, and the therapy CBT and MDR is between group. Okay. Okay. Okay, in this case, you have 3 F tests. Okay, first is therapy. Second is time, and the second one is therapy versus time. This is the 3 factor that you want to measure. Okay. Then a significant result for this therapy indicates that CBT and EMDR differ in their impact on anxiety. Okay, a significant result for time indicate that anxiety change from week 5 to the 6-month follow-up. Okay, and a significant therapy versus time, which is the interaction between therapy versus time, indicate that the two treatment for anxiety had a differential impact over time. Okay, this is something that we can conclude. That is, the change in anxiety from 5 weeks to 6 months was different for the two treatment. Okay, so we can get this result, the interaction result, and for the factor for therapy and a time. Okay, and this is the table that we mentioned just now, which is two-way factorial Anova. These two factor, which is therapy and time, with one between group and one within group. Okay, this is within group, which is the same group of people will do the treatment by time, which is after 5 weeks and after 6 months. Okay. Any question? Okay. Now? Okay. Just now we are in here. So, here. Okay, now we want to extend the design a bit. It's known that depression can have an impact on therapy. Okay, now we want to know the depression can have impact on therapy or not. And that depression and anxiety often co-occur. Even though subjects were randomly assigned to treatment condition, it is possible that two therapy group differed in patient depression level at the initiation of the study. Okay, then any post-therapy difference might then be due to the pre-existing depression difference and not to your experimental manipulation. Okay, this is what we want to extend a bit about our design. Okay, and because of this, depression could also explain the group of different on the dependent variable. It is, we call it as confounding factor. Okay, whether that particular person already have depression, we want to know their depression level. Okay, maybe this depression level have give impact on the treatment, what treatment that they have to attend. And because we are not interested in depression, it called a nuisance variable. Okay, then if you record depression level, we record this. We have another factor which is depression level using self-report depression measures such as the back depression inventory. Okay, this is the measure that we're going to use for this depression level, which is BDI. When the patient were recruited and you could statistically adjust for any treatment group different in depression before assessing the impact of the therapy type. Okay, now we want to know this result, BDI result first. When the patient were recruited, you could statistically adjust. Then we can adjust the treatment group difference in depression. Okay, so we can adjust which treatment that they should go. Okay, in this case, BDI will be called a covariate. Okay, this is the covariate, and the design will be called analysis of covariance. Okay, look what. Okay, this is the link where the covariate means. Okay, then finally you record a single dependent variable in this study, which is from style. You could increase the validity of this study by including additional measure of anxiety such as family rating, therapist rating, and measure assessing the impact of anxiety in their daily function, which is we can uh, add another factor, which is family rating, therapist rating, and measure their impact to their daily functioning. Okay, when they more than one dependent variable, the design is called multivariate analysis of variance, Anova. Okay, this is many dependent variable that we want to measure. Okay, so it called the multivariate analysis of variance. Okay, if there are covariate present, it's called a multivariate analysis of covariance. Okay, then this is all the term. Okay, this is the R side after this. Okay, this is all the term, what is MANCOVA, which is multivariate analysis of covariance. Okay, later, after this, we will use all the tests to measure MANCOVA, MANOVA, and ANOVA, what we call just now, one way, within group, one way between group. We want to use R to measure it, the impact of the particular factor in R. Okay. So this is we fitting Anova model. Okay. Before we continue, is there any question? Are you with me? Okay. This is how we fit Anova model. Although Anova and regression methodologies developed separately functionally, they are both special case of general linear model. Okay, we could analyze Anova using linear. This is the function in R, which is linear model function used for regression. Okay, this is from this book that I attached in the ULearn, which is in chapter 7. They discuss about regression. Then, however, we'll primarily use this is the function for analysis of variance. When we call this, they give the R will give you the significant impact from each factor in terms of their analysis of variance, AOV, meaning that we want to know the analysis of variance in for what we use in this chapter, and the result of LM and AOV are equivalent. Okay, but the AOV function present this result in format that more familiar to Anova methodology. Okay, so for this chapter we will always use AOV because it will represent the thing that we want to analyze. Okay, then for completeness, an example of LM at the end of this chapter is also provided. Then this is the AOV function, analysis of variance. Okay, this is the syntax. And when we call this AOV, we have to put formula. Okay, what is this formula? This formula, you as the one who designed the experiment, you know what is your dependent variable, and you have to know what the factor you want to measure. Okay, then this is the data, which is from which data frame. Maybe you have the graduate infallibility data, and this is the formula for graduate infallibility dependent depend on the independent factor that they have. Okay, then in next table, describe special symbol that can use in the formula. Okay, in this table, Y is the dependent variable and the letter A, B, C represent the factor. Okay, let us, for example, just now, Y, for example, GE, and it's depend on the course. Okay, this is S and A. And if you mention about CGPA, maybe it is B. And okay, C maybe their internship please, and maybe the following factor that we want to know. We want to know course that they take with the intern place. Okay, we want to know this impact. This is the interaction. Okay, then this is the table for the formula. How can we do a formula? Okay, this is the symbol. Okay, this is symbol for separate responsible and left. Okay, for example, prediction Y. We want to predict. Okay, maybe we want to predict, for example, we want to predict banjir contoh we want to know the kadar taburan hujan, we want to know the suhu maybe. Another thing is we want to know the level of the place. This is the factor A, B and C that we want to know. This is the impact is we want to predict whether this place will be banjir in next 24 hours or not, for example. Okay, then this is separate explanatory variable. We separate between two factor. We use plus. Okay, then this is denote an interaction between A prediction of Y from A, B, and the interaction between A, B. Okay, this is the interaction between these two. For example, just now I give, this is you want to predict graduate employability, and this is the cost, and this is the CGPA, and this is the interaction between cost and CGPA. We use the symbol, what we call it, apa double dot ni, colon, semicolon, colon. Okay, then times. Okay, this star denotes the complete closing variable, which is when we put it as this, meaning that if we expand, it will represent this. We want to know the factor from each and the relation between that three, which is AB, AC, BC, and the interaction between A, B, and C. Okay, this is what the symbol of star here, multiplication here. Okay, it's mean this when we expand it, this is the interaction between AB, AC, BC, and this is difference, which is one factor to another factor plus separate the factor. And if we have power here denotes closing to specific degree. Okay, meaning that if we have like this, we expand it, we have this. This is what we want to measure. Okay. Okay, then dot. If we have dot, y depends on dot, meaning that if the data frame contain A, B, C, then we want, instead of we use A, for example, if we have a lot of factor, which is we have around 100. We don't have to put A, B, C, D, A1, A2, A3 until 100 factor, but we just put dot, which is contain all variable in the data frame to predict Y. Okay, any question for this? Okay, later you will use this formula to compute Anova, analysis of variance, based on your case, what you want to know. Okay, if there any question, please ask. Okay, then this is the formula for common research design. Okay, this is when we use Y depends on A. We want to predict Y. We look at factor A. This is one-way Anova. And this is what we call one-way Anova with one covariate. Okay, this X is one covariate. Okay, look back at the previous slide. What is the Anova and covariate? Okay, and this is what we call two-way factorial Anova. Okay, okay, look back. What is when we expand this? Actually, we A times B. When we look at this table, A times B, meaning that we find A, B, then we want to know the interaction between A, B. This is the expand one, which is when we use this. Okay, two-way factorial Anova. And this is two-way factorial Anova with two covariate. Our covariate, we represent it as 1, x2, and this is the factor. And if we have the randomized block, okay, can use where B is a blocking factor. Okay, this is the formula. Then later we will look at the example for the formula that they going to use. Okay, then one way within group Anova. Okay, this is one way within group Anova. We want to know the error subject divided by A and repeated measure Anova within group factor W and one between group B. And okay, this is how we can create the formula. Like previously we learned about algebra, manipulating algebra. We know that we have to calculate sum in the bracket first, then we calculate plus or division, then come for plus and minus. That's also for this formula, the order. It has the order. It is, okay, the order which effect appear in formula matter when A, which is there more than one factor and the design is unbalanced, and B is covariate are present. Okay, if the covariate are present like this, one way Anova, which is it has covariate, we have to put covariate in front. Then we put the factor A. Okay, here when either these two conditions is present, the variable on the right side of equation will be correlated with each other. In this case, there are no ambiguous way to divide up their impact on the dependent variable. Okay, we look at this. Okay, for example, in two-way Anova with unequal number of observation in the treatment combination, the model is Y A times B will not produce the same result as this. Okay, it's different. A times B and B times A. A is totally different. Okay, by default, R employs the type 1 sequential approach, which is this. To calculating Anova effect. Okay, the first model can be written out as this. Okay, the result of our Anova table will assess the impact of A on Y, the impact of B on Y, controlling for A, then the interaction between A and B, controlling the AB as a main effect. Okay, so this is from this model, this is the three impact that we want to know by the Anova. If we put the formula like this, the R result in Anova table will assess these three impact. Okay. So far so good. Okay. When the independent variable are correlated with each other, always covariate. There are no ambiguous method for assessing the independent contribution of this variable to dependent variable. Okay, consider unbalanced two-way factorial design with factor A and B and dependent variable is Y. Okay, then this is the there are three effects in this design, which is A, B, and interaction with A, B. And there are three typical approach for partitioning the variance in Y among the effect, the right side of this equation. Okay. Later in our R, you can see the result for A, the result for B, the result for A, interaction A and B. Okay, the result is on the significant value. Whether A give the significant value or not, whether B give the significant value. If A interaction with B not give the significant value, what we call not give the significant value, which is A interaction with B, the P value from this we obtain greater than 0.05, we notice that this not give the significant impact for Y. So we will focus on these two only. That's the analysis of variance that we have done. Okay. Okay. Hmm. Okay, here. The greater the imbalance in sample size, the greater the impact that the order of term will have on the result. Okay. So, if the imbalance, we have the sample size, for example, for example, for CBT just now is greater than the sample size for EMDR. So we can notice that the greater impact to the CBT will be greater than EMDR. Okay. In general, more fundamental effects should be listed earlier in the formula. in particular, covariate should be listed first. Okay, like you see in the formula just now, covariate as X. Then after the covariate followed by the main effect, whether from factor A or B. Then after this, there is interaction. This is how we list the order of the inside the formula, which is covariate will come first, then this is the main vector too, and this is the interaction between A, B. Okay, then what we want to measure is here. We want to predict is here. Okay, then we'll get this result significant, which is the p-value of this. We have this also. Uh, and also for this, then we can measure, we can conclude something. If the p-value less than 0.05, we know that, for example, this we get less than 0.05, we know that these two main factor give significant impact to predict this dependent variable. Okay, that's what we want to see. That's what we want to analyze later in R. Okay, so far so good. Okay. Okay, for main effect, more fundamental variable should be listed first. So we have to determine which variable is more fundamental. For example, gender is more fundamental than the treatment. Okay, maybe after gender, we want to know the age, for example. Okay, this is the two which is more fundamental. Then the treatment will come. Okay, which treatment? Okay, this is the more fundamental. Like you can see in survey, for example, the after we look at the gender, age, then the more fundamental thing that we want to know, we will list it first, right? Okay, then here the bottom line, when the research design isn't orthogonal, that is when the factor and all covariate are correlated, be careful when specifying the order of effect. Okay, then, okay, here, we go for the lab. Okay, in one way Anova, you are interested in comparing the dependent variable means or two or more group defined by categorical group factor. Okay, here in our R, after this, we want to know our example from cholesterol dataset. This dataset already uh, in R, then in the home package taken from this, the author for this package. Okay, then 50 patients receive one of 5 cholesterol reducing drug regimen, which is okay, this is 50 patients receive 5 cholesterol reducing drug regimen TRT. Then there 3 of treatment condition involve the same drug administered as, okay, this is 20 milligram once per day, one time, 10 milligram twice per day, 2 time, and 5 milligram 4 time per day. Actually, all the drug that they will consume for the treatment is equal to 20 milligram. But the difference is, this is by taking 20 milligram at one time, and this is by taking 20 milligram two times, which is 10 milligram once, and for the second one is 10 milligram. So the total is 20. Also for this, we consume 5 milligram for 4 times. So the total, even though they use it for 4 times, it's still 20 milligram. We want to know, is there any impact? if we take it in a small dose, but frequently. The two remaining condition, which is drug D and drug E, represent competing drug. We want to know drug D and drug E impact. Then, which drug regimen produce the greatest cholesterol reduction? Okay, the response. Okay, this is, we want to know whether drug D or drug E, and by taking it in how many times for 20 milligram will give the greatest cholesterol reduction. Okay. The analysis is provided in the following list. Okay, this is the list. Okay, before we go for that, okay, look at for today R. Okay, let's us run. What can we conclude from that? Okay, let us look at the file for the today lab. Okay, let's open our R. Okay, let's share. Okay. Okay, cancel first. Okay, let me share my R Studio. Can you see my R? Okay, so for this case, we want to know which drug regimen produce the greatest cholesterol reduction. Okay, so this is the treatment condition, 3 treatment condition, and this is the drug that you want to know the effect. Okay, then we go for R. First, you have to install packages malform. Just run it. Just wait for the R to successfully download the package. Then we call malform library. If you have question, you may ask whether you want to open your mic or you want to type in the chat. Then here we attach the cholesterol data frame. If we want to know the function attached more detail, you may search here. Okay, and this is attached to cholesterol. Okay, we already attached the cholesterol, and this is the table TRT. Okay, this is in this cholesterol table. There are data frame. There are table TRT. Okay, what is TRT just now? 50 patient receive 1 of 5 cholesterol reducing drug regimen. Okay, this is the TRT. Okay, this is the table TRT. Okay, here. Okay, let us go. Later I will explain one by one. Okay, and this is one time. Okay, we have a different group, which is we have 50 and 10 for one time, 10 for two time. Okay, this is the head of cholesterol table, and this is TRT one time. The response is 3.8612. Okay, then this is the aggregate. The aggregate by function mean. Okay. Okay, if they take it by one time, so we get the mean is 5.7 and two times 9.22 and four times for 12.37, and this is the different drug that they take, and this is the response mean. Okay, then this is also by look at aggregate for their standard deviation. Based on this is the value for standard deviation. Okay, then this give the Anova, which is this is the dependent variable, and this is the TRT. We want to know the TRT impact for the response. Okay, here. Okay, then if you want to look more detail, you just put summary. Okay, this is the result. Okay, after this I will explain one by one. And okay, just run it first. This is the library for Gplot, and this is if you want to plot it, X for treatment versus Y for response, and you can plot. You can get this, and this is we detach cholesterol. Okay, then I will explain. Okay, this is what we get just now. Okay. Okay, here. Okay, for one, okay, this is the output. As you can see, we have just now in our slide, we mentioned that we have the TRT, which is we have 50 patients receive of 5 cholesterol reducing drug. Okay, then we for the first line, we want to know the group of that particular sample. Okay, the table TRT give you that 10% receive one time, which is 20 milligram at once, and 10% will receive two time, which is they do it which is they take it first for 10 milligram and second for 10 milligram. Then this group of people only take about 5 milligram per for 4 times. This is for 10%. This is for the group. And 10 people will receive drug D and 10 people will receive drug E. Okay. Then, okay, number 2. This is the aggregate. The aggregate. This is the head of our cholesterol table. And this is the aggregate. Okay. This is the group mean. Okay, and then this is the means is appear that drug E produce a greatest cholesterol reduction. Okay, by looking at the mean for the response, we can conclude that drug E produce the greatest cholesterol reduction, whereas one time, which is one time produce the list. Okay, we notice here that the response for those who take it one time, the least one. Okay, in term of mean. Okay, then here, standard deviation were relatively constant across the 5 group. Okay, we look at this standard deviation, it look more constant because the value is not much different to one to another in terms of standard deviation. And the last one, this is the Anova F test. Okay, so we know that here, okay, this is the third, this is 3 star, right? 3 star meaning that it is more closer to 0. This is significant code, which is this TRT test F test for treatment TIT is significant because it's less than, okay, this is like 9.82 times 0 power of negative 13, which is we have about 9.83 Okay, times 10 power of negative 13, which is if we move the perpuluhan to the front about 13 place, we notice that it is less than, if our p-value is 0.05, so it is less than 0.05. Okay, so it is actually it is more or less to 0.01, which is significant enough that providing evidence that the 5 treatment are all equally effective. Okay, maksudnya semua ni all the treatment is not all equally effective, meaning that their effectiveness is not equal. Okay, they have the variance between the treatment. Okay, then if we plot it here, okay, then when we plot it by using the G plot just now, okay, a plot of treatment means with 95% confidence limit. Okay, provide in this figure. Okay, this is the treatment difference, which is we notice that drug E received the more meals compared to the for the response and compared to the one time. Then we can see from one to another treatment is significantly different. Okay, any question? This is the example. Okay, let's look at our notes again. Okay, this is what we received just now based on the significant value. Okay, and this is the table that we get just now. Okay, so we know that this p-value give the variance, which is it show that between one to another factor give different impact. Okay. Looking at the output, you can see that 10 patients receive each of the drug regimen from the means. Okay, this is what we discussed about the output just now. Okay, this is the plot mean. Okay, already discussed about it. And this is the standard deviation between this point. And we found that our Anova test is significant less than 0.001. Okay, this is the plot mean function. Okay, for until here, you know how to use this significant value in your study? Is there any question? Do you want to get more example? Okay. Hopefully, all of you will understand. But if you want me to do some explanation for other example when we use significant value, or if not, I will continue. Okay, this is where the Anova F Test for treatment tell you that 5 drug regimen unequally effective, but it doesn't tell you which treatment differ from one another. So it only tell you they are not equally effective. Their effectiveness is not equal. Okay, we have one question from the chat. Okay. true, Isa? Which is when it is less than significant value, reject as known, which is no difference. There is no difference. So Isa gives statement, is not a question, right, Isa?
Yes.
Mm.
Computational is no difference or equals. Less than significant values we reject means there's a difference, there's a variance.
Oh,
Right.
yeah.
If less than significant value means there is a variance between the
There is a variance, right?
there's a variance.
Okay. Thank you, Isa, for the explanation. Okay, then we continue. This is when we have multiple comparison. Okay, when we have multiple comparison, okay, the Anova F Test for treatment tell you that 5 drug regimen are equally effective, but it doesn't tell you which treatment differ from one another. Okay, then you can use multiple comparison procedure to answer this question. Okay, this is one of example which is to KHSD is a function to test all pairwise difference between group mean. Okay, so later we'll get this kind of table, but we can run our code in R here for this slide. Okay, we have this multiple comparison by using 2KHSD fit. Okay, let's run it. We want to know the use multiple procedure to which is we want to know tells you that the 5 drug regimen, but it doesn't tell you which treatment. Okay, we want to know the which treatment differ from one another. Okay. Then here, okay, this is the function of, okay, later we'll explain. Let's just run it first. Okay, this is by using to KHSD fit. Okay, then here we use what we want to know the difference between when we use this GLHT. Okay, and let's just run. Okay, and okay, before we okay, this is by using 2KHSD fit. Okay, now we get this kind of table. Actually, this kind of table is represent our which is between 2 times the interaction between 2 times and 1 time. The interaction between 4 times and 1 time. You want to know the interaction. Okay, here. This is the lower, which is here. For example, we get this first line, what this graph represent. Okay, this is the lower bound and this is the upper bound, and the difference here is 3.44. Okay, this is the middle one. Okay, this is the different 3.44. Okay, now sin goes to 4 times to 1 times. But this graph only state this interaction between these two. We can't get the full what we want to know, which one is more what we call? We want to know the interaction between one to another. For example, here, the mean of cholesterol reduction for 1 time and 2 time not significant. Because of this is the p-value. Okay, this is the p-value. And whereas the difference between 1 time and 4 time, we look at this 4 time and 1 time, so it is significant. because the p-value is less than 0.001. Okay, then here we can see that, okay, Turkey HST function has compatibility issue with HST package also inject. Okay, we fail in this case. Okay, we use this. Okay, we plot it by using this. We want to know it's more clear. We use the function GLHT. Okay, what is this function? GLHT is the Malcolm package provide a much more comprehensive set of methods for multiple mean comparison that you can use for both linear model. Okay, then okay, here let us look at what this CLD plot for this. After we get the GLHT function to feed it, then we plot it by using the box plot. Here. Okay, let us load it. Okay, then we get this. Here. Okay, here. Actually, these box plots come from this value also, but here it give more information, which is can see that in our box plot, okay, so have the same letter that, okay, group represent a box plot that have the same letter, don't have significant different mean. You can see that 1 and 2 time are insignificantly, which is 1 time and 2 time insignificantly because they have the same A. They share the same E here. And we can see that from 1 time to 4 time it is significant because there are different, which is they not share the same letter. That's the letter means. And this is from 1 time to drag E is also significant, but for 4 times with drag D is not significant. We can conclude by looking at the letter that appear here. If they share the same letter, so for example 1 time and 2 time, it is the interaction between 1 time and 2 time, it is not significant. Okay, when you have this box plot and this letter will give you that information. So when you look at the significance between between the interaction between 1 time to drag A, we can notice that it is significantly different. Okay. So far so good. This is the difference between by using the first graph just now and this graph. Okay. And this multiple comparison methodology is a complex and rapidly changing area of study. To learn more, you can see breadth, fonts. Okay, so this area is still have some improvement. You may, if you are studying in statistical area, you may improve some algorithm for this. Okay, so next we will go to the next slide. Okay, this is the explanation that we go through just now. This is by using the first graph. We see the interaction between 2 and 1. Okay, but we can't see the significant more clearer than we use this. So it's more clear when we share the same letter, so it is not significant. And if they not share the same letter like this for 4 times and 1 time, so it is significant. Okay, let's do the next.
But the letter ABCD is printed by R.
It's printed by R. This is what we plot just now.
Group by R, not
It's grouped by
auto
R.
by R.
Okay, it's grouped by R. We no need to give them this information. So they automatically give you this group. Okay. Or if you don't want to plot the graph, you may put some conclusion by look at the p-value here. But if we have a lot of data, it's quite tough for us to know the significant value, right? So this may make the thing easier for you. You want to know from one factor to another factor, is there any significant value? Yeah. So it's depend on you how you
again, doctor, if like A and B group together means it's significant or not significant?
A and D. Okay. Actually it is represent like okay. It is not A and D. So it is the interaction between 1 to drug E.
Okay, so
To
there's no
drug E.
significant, right?
Drug E. If you can see here, drug E and one time. Drug E and one time. Okay. So it is really significant because it's different, right? And from this value, we know it not share the same letter. So it represents it is not significant. Maybe for if you have one data, you only have this kind of graph. You don't have this kind of graph, but you know this is the factor that you want to measure. So we want to know the interaction between one time with drug E, one time with two times, one time with four times. You can look at this letter. If they share the same letter, so it is not significant. You get what I mean? The simplest way is when we have a lot of data, for example, we don't want to look at the number for the p-value, for example. Okay, we just look at this A, B, C, D group by R. Then we know that, okay, from one time to drug E interaction, there is significant value here. The interaction between 1 and drug E. If you want to more confirm, look at this value by typing AOV formula, this fitting model, okay, which is actually this is the formula. Okay, then you can see the value. But if you only have this kind of graph, just look at the group by R here, A, B, C, D. If they not share the same letter, so we know that it is significant. The interaction is significant. Okay. Are you good? Can't see your face so that tak tahu whether you are good or not. Faham tak?
I just want to review back my understanding. So if not significance means not significant means it's inside the normal value, right? If significance is outside the normal distribution.
Yeah, if it is significant, so the p-value is less than 0.05 or 0.001 that you set.
If more is significant. So it's
if it is less, it's significant. Less than p-value. Because if the p-value is big like this, so we please see this 1, 2 time and 1 time. 1 and 2 time this. they share the same letter A, right? So it is not significant if you want to compare this data with this graph.
Yeah, I get, but sometimes it's confusing.
I know. Because first time I'm studying this, also confused. But the simplest way, actually, I want to make one example from my study, which is I'm doing image processing algorithm. Okay, what I'm doing with this p-value, what I can conclude, okay, for example, I want to make H, this is H. H is my prediction, which is if I can get the improved age, so what is the factor to get the improved age? Okay, I have the previous study. This is previous study, and this is my study. Okay, so I do two comparison. You get it? Which is this is one factor and this is another factor. We want to know it on the impact of age that I get. Okay, actually, I'm doing image processing and it involves data also. And I want to look whether my algorithm that I built is significant enough or not. That's my concern. Okay, that's my objective. You get me? That my study. Then after I get this result, okay, I have, for example, I have 200 image. Okay, I do the previous algorithm, I get this kind of result, this list of result. And after I'm doing my algorithm, I get this. And to measure whether my study is significant enough from the previous study, so I have to get the p-value. If my p-value is less than 0.05, so I can say that my study is significant enough compared to the previous study. That's what I mean. Because sometimes from my data, sometimes in this particular image, they better than me. But in this particular image, they weak, which is me, my algorithm is better than them. So we want to know the difference, which is whether this study is different, how the impact of this study compared to others. That's where I use p-value. You get me? That's the thing that I use p-value to test whether my study is significant enough compared to previous study to improve the age for the image. So this is the thing that they do, which is the drug or the one time or two time of interaction between whether between 4 times to 2 times, is there any significant value, which is so it is not significant. So there is drop E and 4 times, and this is more significant, which is between these two interaction. It is more significant. Okay. Understand or not? Okay, if you not understand, maybe after this you may see back my recorded, and you can see the book that I attached there. All the exercise is from that particular book. Okay, so we may continue. Okay. Later, when we get more code that we use for this analysis of variance, maybe you get some some idea what the p-value will mean for your experimental design. Okay. Okay, this is where the graph box plot that they give. Okay, actually they want to give you a comparison, which is from here we can't see the significant value, but this is give the clear explanation between interaction between different times and different drug that the patient take for the cholesterol. Okay, you can see that cholesterol lowering drug in 4 times was better than taking 20 milligram dose once per day. This is the result that we can conclude after we get the study, which is the p-value. Whether we want to use this list of table or we want to represent it by using this graph, or we want to look at this graph but referring back to this p-value. It's depend. Okay. Okay, now here this is the explanation. Okay, the competitor that wasn't superior to this 4 times per regimen, but the competitor drug E was superior to both drug D and all 3 dosage. Okay, because just now we can see also the drug E means is also more superior to others, right? The means value which is here. The value it represents something. Okay, drug E is more superior than others. So that's why our drug E, the means here from the box plot, it shows that it is 20 value and it is superior from others 1 time, 2 time, and drug D. Okay, then this is what we call, just now we do it this is what we call the multiple comparison methodology. Okay. And this author said it's also complex and it still change in this area of study, and this is how we assessing test assumption. Okay, as we saw in the previous our previous chapter, okay, in this book, okay, our confidence in result depend on the degree to which data satisfy the assumption underlying the statistical test. Okay, in one way Anova, the dependent variable is assumed to be normally distributed and have equal variance in each group. Okay, this is another plot, which is QQ plot. To assess the normality assumption. Okay, then the data will fall within the 95% confident envelope, suggesting that the normality assumption has been met fairly well. Okay, we can see that here, if we plot it by using R, okay, this is where we check the normality. Okay. Here, this is we call the library car. If you can't call the library car, please install the package car first. And here is QQ plot for the linear model response. This is TRT for the response, and our data is from the cholesterol table. Okay, and this is the QQ plot. Okay, here. Okay, here we do the Bartlett test. Okay, let's run it first, then I will. This is for you to know the homogeneity of the variance. Okay, then we check the outlier. Okay, this is the outlier test. and we feed it. Then we notice here there is an A here, which is there are no outlier here. Okay, this is for the QQ plot. Okay, this QQ plot require the LM, which is linear model. To feed it, the graph is provided as this. Okay, look at this graph. And the data will fall within the 95% confidence envelope, suggesting that normality assumption has been met fairly well, which is we can see that this data is around this line of linear model. Okay, so we can suggest that the normality assumption has been met fairly well. Then this is for the test of normality. Okay, then R provides several tests for equality, which is homogeneity of variance. For example, you can perform this Bartlett, which is where the Bartlett just now. Okay, the Bartlett test. And this is the code for the Bartlett test for the data cholesterol just now. Okay, then this Bartlett test indicate that the variance in the 5 group don't differ significantly. Okay, it is not differ significantly because for the 5 group, they don't have the significant difference because the p-value here is 0.97. Okay, other possible tests indicate the Fitner-Killen test provided by the Fitner test. Okay, then here, if you do the library car, we want to know the outlier for this data. Okay, we do this outlier test function and we call fit again. Fit just now we use it for where we find the fit. It's just this is the fit just now, which is we find the Anova response for TRT for the response, which is this is the dependent and this is the independent, and we call it as a fit. Okay, now here we want to know whether in this fit has outlier or not. Okay, we do this outlier test for fit and we can find that there is no which is not available. For the output, you can say that there no indicate outlier in the cholesterol data, which is when P is greater than 1. Taking the QQ plot, Bartlett test, and outlier test together, the data appear to fit Anova model quite well. This in turn add to your confidence in the result. Okay. Okay, so this is how we assessing our test assumption. Okay, then we proceed. Okay, this is just now the homogeneity test. Okay, because we want to know the normality just now, right? Okay, we can use this assessing test assumption. We want to know the homogeneity of our data. We want to know the outlier for our data just now. We can use this outlier test. Okay, so this is for one-way Anova. Okay, this is one-way analysis of covariance. Extend the one-way Anova to include or more quantitative covariate. Okay, previously in the first few slides, we just know, understand the term that we will use, and now we will use this term to test it in R. Okay, so here is one-way ANOVA. Okay, one-way analysis of covariance extend to the one-way ANOVA. Okay, include one more quantitative covariate. So we have covariate here. Okay, this example come from the little data set in the Marcom package. Okay, here pregnant mice were divided into 4 treatment groups. Each group received a different dose of drug. Okay, so here our sample is pregnant mice. Okay, so we give these pregnant mice with 0 drug, 0 dose of drug, and 5 dose, 50 dose, and we increase it as 500 dose. And for these 4 treatment group, okay, so our sample is pregnant mice. We divide it into 4 group of treatment, and they will receive this different dose of drug. Okay, so the mean post-birth weight for each liter was the dependent variable. Okay, the mean post-birth weight for each liter was the dependent variable. Okay, so this is our dependent variable, and gestation time was included as a covariate. So look at our code. Later we get this. We have these 2 factors, which is gestation time. We have this gestation time, and we want to know the effect of gestation time and the dose it takes. Okay, so let us run R. Okay, here. Okay, we use the data liter and from the package Malcolm. And this is we attach liter. Then, okay, this is aggregate, where here we get the sum of the value in terms of mean. Okay, sum of each group. Okay, this is table. Okay, this is table of those, which is we notice here that we have the different sample for each dose, which is for no drug, 20 sample, 5 drug, 5 dose of drug is 19 sample, 50 drug, 18 sample, and 500 drug, 17 sample. Now aggregate. We want to know this aggregate weight for the liter in terms of mean. Okay, so we can see that the 0 drug will give 32 mean. Okay, so it gives the higher mean. So from the previous slide, we noticed that the greater the sample that we take, it will impact also in our response, right? So this is one of the example. Okay, but the 0 dose of drug really means something to this data, this experiment. So here we want to feed it. We define analysis of variance, and we name it as a feed, and we want to know the summary of feed. Okay, here. How can we conclude this? Okay, here. Okay, from the table function, okay, you can see that there are unequal number of liter on each dosage level. Okay, for 0 dose, okay, there are unbalanced, right? Unequal number of liter. Okay, with 20 liter at 0 dosage, no drug, 70 liter for 500. Okay, 70. Okay, based on the group mean provided that by aggregate, we get the function mean here. Okay, the no drug group had a highest mean liter weight with 32.3 weight. Okay, then when we are doing the Anova F test, okay, here indicates that, okay, we add the covariant gestation time into the factor dose, right? Okay, then here gestation time was related to birth weight. Okay, for A, gestation time was related to the birth weight, and drug dosage was related to birth weight after controlling for gestation time. Okay, because we can see that this two p-value is less than, is smaller, which is it gives significant impact. Then the mean birth weight isn't the same for each the drug dosage after controlling for gestation time. Okay, because you are using covariate, you may want to obtain adjusted group mean. Okay, now, just now we adjust this group by their mean. Okay, now we doing this effect package. Okay, so in this effect package, we want to make some modification for this data just now we only use from sample, but we want to change from the effect of mean for each of the group. Okay, so we call the library effect. Just wait. Okay, then we use effect those fit. Okay, then this is the effect, which is we using the mean. Okay, the mean that it provide here. So we use it to know the impact for the each dose. Okay, we do some modification. This is just simply take the sample value, but here we use effect of the dose to the fit. Okay, then for the multiple comparison, okay, we can use the library Malcolm, and we set the drug contrast. Okay, you can see that this contrast 3 is more, the one is different, which is we want to know the contrast between no drug with drug. Okay, because we want to know the no drug versus drug here. Okay, then the summary for this. Okay, we can see that this significant, this result based on the p-value is also significant because it is star here, which is less than 0.05. Okay, so we can see that there is we can see that there is a significant value with no drug versus drug. Okay, okay, by comparing these two. Okay, okay. Additionally, the Markov package can be used to test specific user-defined hypothesis. If you have the specific user-defined hypothesis to compare the multi-comparison, you also can use it. Okay, then here you can see that this is the dose effect. If we want to see the okay, this is just now I already mentioned that this is the contrast, right? They want to show you the contrast between no drug versus drug. First group with the average of other three. The hypothesis is test is that with a t-static 2.581 in this case, which significant as p-value is less than 0.05. Okay, therefore you can conclude that the no drug group has a higher birth weight than drug condition. So this is the conclusion that you may conclude, and other contrast can be added to the R-bind function. Okay, this is our binding just now. So other condition you may change this. Okay, this is from no drug to versus drug, or you might want to see the most drug to the lowest drug or no drug. You may use these three, and others with -1 also can use. You want to see the contrast for that. Okay, then how can we assess test assumption for this? Okay, this is one way Anova just now. We do it in a lab, and this is the this is gestation time and dose. Okay, the Anova F test indicate the gestation time was related to the burst weight, and drug dosage was related to burst weight after controlling for gestation time. Okay, and this is that we do the effect for the based on each group based on their mean, and this is the we want to know the one way the result for this effect. We can use the aggregate function. Okay. The aggregate function that we used previously is to get mean for each group here to do the effect. Okay. Then this is the one way Anova example. Okay, this is what we do just now. Test specific the undefined hypothesis about the mean. Okay. Okay, maybe you want to proceed with this no drug condition differ with 3 drug condition. Okay, this is what we learned just now. We want to know the comparison with no drug to the 3 drug condition. We use this formula, and here we state this 3 -1 3 with the no drug, and we state the contrast value the other drug condition with -1. So we want to know the impact no drug with others. Okay, and this is how we test the assumption. Okay. We want to design make the same normality and homogeneity of variant assumption described for Anova design. You can test this assumption using the same procedure. So previously you also used the assessing test assumption also, but in addition, standard Anova design assume homogeneity of regression slope. In this case, it assumed that the regression slope for predicting birth weight from gestation time is the same in each for 4 treatment groups. Okay, a test for homogeneity of regression slope can be obtained by including a gestation times dose interaction in terms of Anova model. Okay, here look at this. We after this we look at our R. We notice that we put the factor as a gestation time, dose, and gestation time relation with the interaction with the dose. Okay, so now from this table we notice that this two is not significantly give the significant impact, which is less it's greater than 0.71. The p-value is 0.17889 here. Okay, here if we can see the interaction for the homogeneity regression slope. Okay, so let us run, and you can see that fit 2 here, instead of using gestation time and dose, but here we want to know the relation between gestation time and dose. And you can find the fit 2 summary here. Okay, gestation time and dose. Okay, because of it is time, actually when it is time, look at the formula just now, we only put time, but get the data for first factor, second main factor, and the relation between gestation time and dose. Okay, this is the formula, and this is the information that we get. We can see that here, okay, the interaction is non-significant, supporting the assumption of equality of slope. If the assumption is untenable, you could try transforming the covariate or dependent variate using a model that accounts for separate slope, or employing a non-parametric Anova method that doesn't require homogeneity of regression slope. See the other function, which is sm.Anova here. So if we look at this, install the package, we want to visualize this result in terms of gestation time and dose. We can visualize it by using HH library here. Okay, this is the data that we get, the table. Okay. Here we can see that the regression line for predicting birth weight from gestation time are parallel. You can see that this parallel from each group, but have different intercept, which is we put here intercept with the line here. It is different from one to another. Okay, as gestation time increase, birth weight increase, which is we can see that gestation time increase, the birth weight will increase. Okay. Additionally, you can see that zero dose group has the largest, which is this zero dose group has the largest intercept, and the 5 dose group is the lowest one. The lines are parallel because you specified them to be. Okay, because we use gestation time times dose just now. So that's what we said by ourselves. That's why we found that the line are parallel. Okay. Okay, here this approach is useful for visualizing the case where the homogeneity of regression slope doesn't hold. Here is the graph for the whole, to represent whole those with the different group, which is this is the highest one, and from the fifth group, the lowest one. Okay, the purple one is the lowest one. The 5 dose group is the lowest one. Okay. Are you good? So we are here. Maybe we can see the book. What we call the author here is Kabakov, to get more explanation for this experiment. Actually, for the first phase, in the first lecture just now, I already mentioned about all the term and all the difference between one way for within group, between group and other term. And this is where the experiment use data from the just now to study about the weight, and this is for the condition, which is we want to know the cholesterol, we want to know the reducing drug regimen. Okay, by using the 5 cholesterol reducing drug regimen, and until here, we get the significant. Okay, we can see that this, the gestation time interaction with this dose is not significantly, is not give the significant less value, p value less than 0.05. So we can we can conclude that these two give the impact for the weight compared to the relation between gestation time and dose. Okay, then this is how we visualize the result. And I think I stop here, or you want to proceed? Maybe we can continue on the next class on Thursday. And if you have some question from this today class, you may ask also, because I think there's a lot of things already give to you today. Just look at it one by one, more slowly, more which is tengok, perhati betul-betul, fahamkan balik, then maybe the next for two-way factorial Anova, we can get what the R value give to us to the value that we want to measure. Okay, so we stop for at this two-way factorial Anova. Can or not? Okay.
Okay.
Is it? Are you okay?
We continue on Thursday.
Okay, continue on Thursday. Hopefully, or all of you get something from today's lecture. It's quite different with learning mathematics and statistics, because a lot of sentence in statistics that we want to conclude something, that we want to have to know what is our objective. That's the thing in the statistics. Thing that we have to know first before we are doing our statistical test. Okay. So see you on next Thursday. Thank you.
Thank you, Rada.
Thank you, Doctor. Bye-bye.
Bye bye.